So I'd like to move on to another aspect of what's coming up for the Personal Space Weather Station, and that's Jonathan Rizzo, who's going to be talking about VLF measurements, specifically a VLF module for the Tangerine SDR. So he's going to give us a progress update. So Jonathan, the floor is yours if you can share your slides.
Hi, everybody. Okay, let me share the PowerPoint here.
Great. And I will give you a 2-minute warning as usual.
Okay, good. Okay. Okay, can everybody see my screen?
It has not clicked into presenter mode. It's still the. You can give it like this, which is fine, but okay. And then you need to. Yeah, you need to switch between. Go to the swap displays button up there at the top, because we're seeing the presenter mode. You click on this. It's the third button on the top of your screen, and then there's a. There you go. Perfect.
Oh.
You can give it from there. It's fine.
Yeah, this is fine. I apologize for that.
That's okay. Go ahead.
All right, hi everybody. My name is Jonathan Rizzo, KC3EEY. I'm a University of Scranton alum and a VLF enthusiast. And I'm giving a progress update on the VLF module for the Tangerine SDR. So what I wanted to do was I wanted to started with the inspiration. A post on the Natural Radio, on the VLF Natural Radio groups.io group about the performance of the Behringer UMC 404 HD professional USB audio interface as a DAC instead of a high PC sound or a high quality PC sound card kind of sparked my interest in this. Paul Nicholson, the author of vlfrx-tools, which I'm going to get into soon, he liked it so much that he used it in his production reception system, replacing his M-Audio 192 PCI sound card. It utilizes the Cirrus Logic CS4272 24-bit 192 kilohertz stereo codec for analog and digital conversion, and it has 114 dB dynamic range. This was great, but it's a codec, and I did not want audio inputs and outputs for this project. So before we continue, I want to get into what vlfrx-tools is and how this module is going to operate in synergy with vlfrx-tools. It's an open source VLF radio receiver toolkit for capture, analysis, and storage. VLF receiver audio it is fed into your sound card, and this could be a high quality sound card, as well as the GPS pulse per second signal. It can't be fed into the serial port or parallel port because there's too much latency. So it captures VLF receiver audio from your VLF receivers, and it applies a GPS timestamp. It automatically filters out power line hum with a tracking filter. So it actually tracks the minute variations in power line frequency as the day goes on. It detects Whistler and chorus events automatically, and it can do lightning location through the time of group arrival method. It supports triple axis reception. So you have your E field, north, south, B field, and east, west B field receivers. It can detect sudden ionospheric disturbances, varying distance of VLF signals. It's open source, and you could compile it on Linux, FreeBSD, or OpenBSD. And you could also set up an IceCast server for live listening. This is a block diagram of the how the utilities in this tool set will be set up. You have your E-field receiver. along with your GPS receiver outputting PPS, and it goes into a utility called VT card, and that will capture the audio and timestamp it according to the system clock. VT time finds where the GPS pulse per second is in the audio signal and adjusts those timestamps to be aligned with UT time. VT filter filters out the mains hum and any other sorts of filtering that you need. The streams are combined with VT cat. VT event can automatically detect whispers and chorus. VT toga is for lightning location, and VT Vorbis allows you to stream to an IceCast server. So it's a very very good tool set. The inspiration, what I wanted to do was I wanted to use this ADD converter, but as I said, it was a codec, and you'd need two because it's only 2-channel. So instead, I chose to use the CS5364 that has 4 analog inputs, and they're only inputs. And for the Tangerine SDR, it would obtain its master clock from the GPSDO and generate audio samples via I2S or TDM port into the FPGA. It interfaces to the leaf board through the data engine through the leaf board. You connect your VLF receivers to screw terminals on the board through audio isolation transformers. That's extremely important. You would pick your sampling rate, your sample length, and the FPGA will configure the clock module to generate the appropriate clock. The samples are transported into the FPGA, and the FPGA will timestamp each sample reference to GPS time in the same way that VT card timestamps against the system clock, and it makes it available as a TCP or UDP socket that you could connect to another computer down the chain. And it combines multiple channels, your E field and your B field, into one stream, and it aligns those timestamps, each of those channels. But there was an issue, as you can see here, it has different sampling speed modes, and the problem is that the digital filter tends to roll off at about half of the sampling rate for the first 2 modes. That means that we wouldn't be able to get 100 kilohertz operation for people who wanted to monitor VLF transmitters. And as you can see, the QSM, that's the highest sampling rate. That's actually 0.25 of the sampling rate. So we wouldn't be able to get those higher frequencies all that well. So instead, what I did was I chose the Texas Instruments TLV 320 ADC 6140, or the 6140. That has a maximum sampling rate of 768 kHz, 4 ADC inputs only, and it has a 122 dB dynamic range with the dynamic range enhancer, and 112 without. So that's pretty good performance. It has 3.3 volt to 1.8 volt IO-VDD operation, and we're going to have to use 1.8 volt for the leaf module, and its filter performance is much better. This is a basic schematic of the circuit that I will be using. This was taken from the evaluation board. Just ignore this down here. But you have your 4 inputs here. So this is where your audio isolation transformers are going to connect. You have your different voltage rails, and you have your digital outputs here, which are going to connect to the FPGA. It's actually really basic. There's nothing really more than this other than power, because it's a very all-in-one type of chip. So you don't really need much externally. For power, what we're going to use, we're going to use the TPS 735-Q1. We're going to use the 1.8 volts fixed version. And the good thing about this, it has similar noise and thermal performance as linear technologies LDOs, and it costs less than half. So that was a very good choice. As a side project to this, I will be designing a sound card for the Raspberry Pi and the Onion Omega 2 Plus. This is going to work similar to the audio injector high performance sound cards for the Raspberry Pi, but this is only going to have inputs, and it's it will be for direct use with vlfrx-tools. The reason why that I want to use the Onion Omega also is because it's a smaller footprint, even lesser power IoT computer. So this would be really good for deploying in the field on battery power. It uses a much less power. And a anecdote from Paul Nicholson. This is really cool. This is what really gets me excited. This was when gravitational waves were detected at LIGO. Paul says this: I'm pleased to report that our VLF receivers played a very small part in this. On October 17th, we got a request from Dr. Robert Schofield looking for VLF data for a specific period. He didn't say what it was for, but it was easy to put 2 and 2 together. And what he wanted to do was he wanted to check the VLF spectrum for any spherics that might cause a false detection. Paul on his stream server did not have enough backup for the time period that he needed. But there was another volunteer who had high quality 192 kilohertz sampled VLF data on his computer for the time period needed for Dr. Robert Schofield. So these VLF receivers were built from the basic parts, less than $20 in parts, and a $35 sound card from eBay. And he was able to take high quality measurements that was used in one of the most amazing discoveries in recent times is gravitational waves. Really, really cool. Phil, how much time do we have?
It's 12:16. You have a couple more minutes, and then actually 3 or 4 minutes if you'd like, and then we have time for 3 minutes of questions.
Okay. What I want to do is I would like to share a quick video here.
Does this have sound?
Yes.
Okay, there is a checkbox you need to check that says share sound when you share your application. Let's be careful about that.
So this is what's called a polar plot. So these are signals from 3 VLF receivers: E field, northwest B field, and east-west B field, combined into a polar plot superimposed with recorded audio. So there's a video here, and this is also what's really cool. And can everybody hear the crackling?
Yes.
Okay. So what this is, so this is north, south, east, and west. And as you can see here, we have spherics coming in over here. This is mains hum, and these are local interference. Over here, we have the Russian Alpha navigation system signals coming in over here. And what's really cool about this recording is that there are whistlers in this. So we can see the direction of whistlers coming in. And this is what really excites me, because this visualizes these VLF signals coming in, where they're coming from and at what intensity. So this is something that can be done with vlfrx-tools, and if we have a 3-channel stream from the VLF module, we can create these types of visualizations. So this is really, really cool. So I will stop that, and I will go back to the PowerPoint. Okay. So I would like to thank everybody, especially any members of the VLF community that attended. I want to acknowledge support from the NSF to the following grants. I would definitely like to thank Paul Nicholson for his endless support, vlfrx-tools, and contributions to myself and the VLF community at large. Also, thank the VLF community for all the wonderful support and motivation. I would like to thank Tom N5EG and Scotty WA2FI for all their technical support with the VLF module. And last but not least, a big thank you to Nathaniel Fursell, W2NAF, for his endless support and motivation for this project. Thank you.
Thank you very much, Jonathan. That was great, especially with audio. That's and video. Quite spectacular. Yes, Deb, we have a couple of questions. Yes.
So what
we have time we have about 2 or 3 minutes.
Yeah, from Aaron Oppenheimer. What is the video filter used?
Can you repeat that again, please?
What is the video filter used?
Are you talking about VT filter?
Video filter.
Yeah, the question says, what is the video filter used? It was about the time maybe you were showing the video, I believe.
So that program uses its own code to generate video, and it encodes it into MPEG-4 format.
Yeah, I guess he's clarified. He says the visualization of the VLF interference audio. So maybe you just answered it. I don't know.
So,
maybe.
Yeah. Another question from Andrea Contini. Can it be done also with higher frequencies? Can it be done with higher frequencies?
Yes, it can. That's why that I chose the higher frequency ADC. Paul Nicholson has a live VLF spectrum that goes all the way up to 100 kilohertz on his website. So these tools can be used for higher frequencies.
Okay, I think we have, that's it.
Okay. Thank you very much, Jonathan. You could probably go look through the chat to see if there's any other clarifications, but thank you very much. That was very enjoyable.